Have you ever wondered what it would be like to travel back in time to witness history or forward to see the future? This question has gripped the human imagination for centuries, sparking countless stories and films that capture our collective fascination with time travel. From H.G. Wells's The Time Machine to the Back to the Future trilogy, time travel is a staple concept in popular culture. But is it merely a flight of fancy, or could it have a basis in reality? Enter the realm of theoretical physics. Here, time is more than just a tick-tock on a clock. It is the fourth dimension intertwined with the three dimensions of space in the fabric of our universe. And according to Einstein's theory of relativity, time is not a constant. It can stretch and shrink, change its pace relative to the observer. So, if time is flexible, could we potentially bend it to our will and travel through it? Now we delve into the realm of theoretical physics, where time travel isn't just a figment of our imagination. One of the most intriguing possibilities for time travel lies in the concept of wormholes. Imagine you're trying to reach the other side of a mountain. You could climb over it, but wouldn't it be easier if you could just tunnel through? That's essentially what wormholes are, shortcuts, tunneling through the fabric of space and time itself. They're predicted by Einstein's general theory of relativity, but they remain purely theoretical for now. The idea is that if we can somehow stabilize a wormhole, we might be able to use it as a bridge to another point in time. But wormholes aren't the only game in town. There's another, perhaps even stranger concept known as cosmic strings. These are hypothetical one-dimensional defects in space-time, thinner than an atom but incredibly dense. They're thought to be remnants from the early universe. And if they exist, they could have some interesting properties. For instance, if two cosmic strings were to pass by each other, they could theoretically warp space-time in such a way as to create a loop, a closed, time-like curve. Travel along this curve, and you might just find yourself back in time. But remember, these are all theoretical concepts. Despite decades of searching, we've yet to find a single wormhole or cosmic string. And even if we did, there are enormous practical and theoretical challenges to using them for time travel. Stabilizing a wormhole, for instance, might require a form of matter with negative energy density, something we've never observed. And cosmic strings, if they exist at all, would be incredibly difficult to manipulate. While these concepts are fascinating, they come with their own set of paradoxes, which we will explore next. Imagine visiting the past and altering an event. Wouldn't that change the present? This is where the paradoxes of time travel come into play, and they are truly mind-bending. Take the grandfather paradox, for example. If you travel back in time and accidentally prevent your grandparents from meeting, you would not have been born to travel back in time in the first place. This creates a loop of cause and effect, a paradox that seems to make time travel impossible. But what if I told you there might be a way around this paradox? This is where the many worlds interpretation comes in. According to this theory, every decision creates a new universe. So if you travel back in time and change something, you would merely create a new timeline, a new universe. In this universe, you might not exist, but in the original one, you would still be there. Then there's Novikov's self-consistency principle, which suggests that time travel could be possible, but only in a way that is consistent with the past and the present. This means any action you take in the past has already been taken into account in your present. A sort of predestined time loop, if you will. So, while time travel holds a certain allure, it's a concept fraught with complexities. The paradoxes it presents are fascinating, yet they underscore the intricate nature of our universe and the laws that govern it. Time travel, as of now, remains a captivating concept nestled in the realm of theoretical physics. We've delved into its intriguing aspects, considering time as the fourth dimension, exploring potential methods for traversing it, and pondering upon the paradoxes that create fascinating conundrums. Yet these ideas are but the tip of the iceberg. The full implications of time travel are still far from our grasp. Until we unravel more mysteries of the universe, we can only dream and speculate about the possibilities of time travel.